Today I'm going to show how to build this more efficient 49-to-1 transformer with the tight wind and the tap on the second turn. Also using the TDK capacitor that we've covered in our previous videos. So stay with us to the end. You'll be able to build one of these for yourself. Okay, we're going to go over the list of supplies that we need. We need two FT240-43 toroids. We're going to tape these together, so you need a little electrical tape. And we need 16 gauge solid copper magnet wire or enameled wire. And this is 16 gauge, that's American. It's around 1.3 millimeters diameter. So for my metric friends out there, 1.3 or thereabouts is the equivalent of 16 gauge enamel solid copper wire. And we need about 70 inches total of that. We'll need about 66 inches or 168 centimeters for the winding itself. We'll need about 4 inches for the tap itself, and then the distance of the tap from one end of the wire is 10 inches. And what we'll do before we actually do the winding is we will measure 10 inches on the wire and strip off the enamel there, because that's where we will end up soldering our tap to. So let's get started measuring out the wire. These little green cutting mats come in pretty handy. My particular mat is 35 inches wide, and since we need 70 inches, I just need to measure twice across this mat and we'll get our 70 inches. Okay, there's once, and there's twice. I'm going to leave an extra couple inches on there just for good measure. Wire is not that expensive, so have a little bit left over on the ends. That's okay. If you happen to hear any noise in my background there, a little whirring noise or whatever, I've got a 3D printer printing something up for me, so hope that doesn't distract from what's going on. So now we're going to cut off 4 inches. That's going to be used for reserved for our tap. So we've got 1, 2, 3, 4. So I'm going to cut it right there. Set that aside. We'll use that for the tap later. And then need to measure out 10 inches back so we know where to strip the insulation. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'll make a mark there so I won't lose it. And we'll strip back the insulation off of that, so we'll have a place to solder to later. And get my knife. You can use a knife or razor blade, whatever, but you just got to get all this enamel. Should be able to see the copper color there pretty well now. It's not hard to get off, it just takes a minute, but that is a better insulation than you might think. You know, this is the same magnet wire that's used in alternators, generators, you name it. Anything that uses a magnetic field, pretty much. This is the type of wire. It may be a different diameter, but this is the type of wire that they use. So, get a little more off right there. You can use sandpaper, you can use a razor blade, you can use whatever floats your boat to get this insulation off of here. And that's pretty good. All the way around there, as far as I can tell. Now what we're going to do is take our little needle nose here put it right in the center of the area that we scraped, and then bend it down on either side like that, and then squeeze it together almost all the way. Take our pliers. Oh, insulation didn't get off. Evidently I can't see, but get that insulation off of there so we can solder to that later. I probably should have bent it first and then scrape the insulation off, but either way should work. So I'm going to stick the end of the needle nose right there and just bend the wire out at a 90-degree from that little bump. And that little bump, or that little loop we're putting in there, is where we're going to solder our tap. Now we can squeeze it together a little more. So how do you wind this thing? Well, first let's tape our toroids together. You have trouble finding the end of the tape like I do. Seems like I can never see it. Alright. Get off about 4 inches of tape. Stack them up. Start it like that, and then pull it tight. Wrap it around, pull it tight. There. That's one side. Do the other side the same way. Doesn't look real pretty, but it's functional, kind of like me. Get the tape on the other side here. Alright, got the two toroids taped together. Now, what we're going to do is take this wire, I'm going to put it right there over the top of that. See, the short end of the wire we'll wrap, that'll be our tap for the center conductor of the SO239, the center conductor of your coax. So we'll pull that through. We'll get this positioned there in the center, just so we have room to work on it. Bending that 90 degrees down there just to help hold it in place. And we'll wrap this tight around here. And there we go. Get this. I like to take a screwdriver or whatever, little plastic handle, and just flatten that out to help get it tight. We'll get it a little tighter as we pull these other windings through. And we need 14 windings. And if I measured correctly, we should have enough wire to do that. We need to try to keep these windings as close together as we can, but we don't want them to overlap. We got to keep each winding in sequence going around here, or we don't get the transformer function as we should. It's just repetitive. Just keep doing the same thing over and over. Pull it tight. Stick it through with your thumb from the underside and then pull it through. We'll straighten out some of these windings, make them look a little better. I don't know if it makes it function any better, but we'll make it look a little better after we get all the windings on here. Yeah, let's stop and see how many turns I've got. I don't think I've got quite enough yet, but we'll count them. Alright, so we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Wow. And let me double check, make sure I counted that right. I have been known to count them wrong. Some of my viewers caught me on that on one of my other videos and I had to correct it. So we can go from this side. It doesn't matter, right-handed or left-handed, but as they go through, we'll count here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, we've got our 14 turns. So I got a little more wire than what I needed, but I'd rather have a little extra than not have enough. Got about a foot too much here. Go ahead and cut that off there. Now, we've got our windings. I'm going to try to straighten some of these that are bent a little bit. And that's going to be fine there. The other thing I like to do is put some wire ties to hold everything in place. So I get this wire tie on here. Alright, cut that one off. And get this one pulled in a little tighter. Try to get them evenly spaced, and do the same thing with the wire tie over here. That way the hopefully hold the windings in place a little better where they don't move. And your readings will be more consistent. It should not change. You know, if you're moving it around, get that pulled tight. So now we've got both leads coming off at approximately 90-degree angle. And this is the lead that will go to the antenna, and we'll have to cut it to length and then scrape off the insulation. This is the lead that will go to the center conductor of the coax, center of your SO239, and then your grounds will come off of this tap right here. And this tap is on the second turn. See, the turn starts here. So this will be one turn. This will be the second turn, and that way we'll get our 49 to 1 ratio, which is what we're shooting for an end-fed half-wave antenna. Okay, that'll work. Now I'm gonna get set up to solder the tap onto here, and we won't have much left to do. Okay, here's the 4-inch piece of wire that we cut off earlier. Just need to strip off about a 1/2 inch of the enamel insulation. Hopefully I'll get it all the first time this time. My eyesight isn't what it used to be. I need more light all the time. Can't seem to focus sometimes, but I guess that comes with being more mature. Alright, there's a little there I need to get off. Alright, so what we're going to do is bend a little hook in this. And then we'll hook it into that loop, and then we'll squeeze them tight on each other and solder them together. So here we got our hook, here we got a loop. So we're going to put the hook inside the loop, squeeze that together, and then we'll also squeeze the loop together. And now we've got a good mechanical, and we'll also have a good electrical connection from that. So let me get my ancient soldering gun. Man, I've had this thing, I think 50 something years. But if I want a lot of heat and I want it relatively fast, this never fails. I get so tired of these little soldering irons, and I've got 3 of them over here, and when I need them, they don't seem to put out the heat. Put a little dab of solder on there, touch it, and then let the solder flow around. I'm going to put some on that side too. Don't want any excuses here. But we've got a good electrical connection there now. Mechanical, electrical, all the way around. This is other style transformer that we're going to compare this against. I've already built one transformer like this, and this is the second one, so we can do a back-to-back test. But we're going to fix it where it will be in a box similar to this one here, so we can use this as a template to cut our wires. I'm going to again cut them a little longer. Right now we just cut off some of this excess. And then I'll strip the insulation enamel from these, and then we'll set up and do our back-to-back test. Okay, I've got the insulation stripped off of the wires now, and I've got our 100 picofarad TDK capacitor just twisted on here, and I'm about to solder those leads on, and then we'll set up and do our test. Wait for the soldering iron to heat up. Put just a touch of solder on it. There. That one's soldered. And so is that one. Now I'll cut off the excess length of those leads there. And now we'll be able to connect this up and run our test. Now I'm going to be using one of these BNC breakout connectors. See, it's a BNC connector there, and then it breaks out the positive and the negative here. So this side here will be the center conductor from our coax, and this side here will be our shield. Then I have the adapter to adapt it down from BNC down to an SMA connector. Put that in. So the center tap is our ground connector, so we'll put it in like this. Yeah, we'll put it in like this. Just trying to think how we're going to connect later, but put it in and just tighten these screws down. That way you get a good connection there. And now we're good on that. That foot of wire that I had to cut off, I took a short piece of that. I stripped the insulation from both ends because we got to connect our ground to our second transformer. So I'm going to loosen this connection right here. Going to put this second wire in that connector, and we'll tighten it back down. And that'll complete the circuit. Now this is the one I showed you at the beginning. This is the one I built previously. It's wound the same way. Got the tap here on the second turn, and we have our TDK 100 picofarad capacitor across the leads here. Our ground is connected here, and our antenna wire is connected here. So all I need to do now is connect this up. And get the antenna lead on here. Got them all tightened up. And that should be our test rig. We've got the capacitor here. Get it up where you can see it. This is both of these are TDK 100 picofarad. We'll get our NanoVNA out here, and we'll see what kind of losses we have on these 49-to-1 matching transformers with the tap instead of the twist, and also with the tight windings instead of the crossover windings that was in this one, where we had 7 turns, a crossover, and another 7 turns. Here, all 14 turns are tightly wound together. That should improve our efficiency by having them wound like this. So let's get the NanoVNA set up to test these 2 transformers. Okay, I've got our test configuration set up here, where we've got the 2 transformers back to back. They're identically wound, have the same capacitors. We got our antennas connected together here. We've got our ground connected together here. And we're going to be feeding this one with a signal. It's going to go through and come through this one and back to port S21 or port 2 here on our NanoVNA. Alright, so let's look at our different bands. I'm going to record it all here, then we'll put it into a spreadsheet and do our efficiency calculations through the spreadsheet. We'll do 1.797 because that's what we used on the previous test. So 1.797, we have a total loss of negative 1.87. And that's at 1.797. Just so we be consistent across all of our tests, we want to use the same frequencies. And I'll divide this by 2. That should be 0.935. So loss through a single transformer would be 0.935. Let's go up to 3.827. There's 3.827, and we have a loss of a negative 1.46. And that's at 3.827. And divide that by 2, that's 0.73. 0.73. Go up to the 40 megahertz, 7.235. There's 7.235. We have a negative 1.29. Divide that by 2, negative 0.645. Alright, let's go on up to 20 meters, 14.267. There's 14.267. We have a loss of negative 1.07. That comes out to negative 0.535. Is that right? I may be a decimal off here. I'll check my math later. Anyway, we'll come back to that. I'll put a star by that and make sure I calculate that. I'm trying to do this in my head, and it may or may not be working. Alright, go up to 17 meters at 18.110, and there we are, and the loss there is 1.05. So again, that's 0.5 and 0. I'm sorry, 2.5. 0.525. All right, let's go on up to 15 meters, 21.300. 21.300. We're at a negative 1.09. Negative 1.09. 21.300. 18.110. Okay, that comes out to negative 5.45. All right, let's go up to 12 meter band, 24.925. 24,925, we have a loss of negative 1.18. Stabilized there now, 1.18. That's a 1. 24,925, 1.18. That's negative 0.59. From what I remember, these are looking excellent compared to the previous transformers that we compared. But we'll do that analysis once we get it all in the spreadsheet. Let's go on up to 10 meters. 28.332 is what frequency I've been using. There's 28.332. Let that stabilize a second. That's negative 1.4, we'll say. Negative 1.40. That's negative 0.70. So we'll get all these entered into the spreadsheet, and then we'll calculate our efficiency, come back and talk about that. Okay, just a quick review of the different transformers that we've tested. The first one was a 49-to-1 with 14.2 turns with the twisted tap, where the primary and secondary were twisted together for the first 2 turns. In all 3 of these transformers, we used 2 FT240-43 toroids, and on the first one we used generic 100 picofarad caps that were purchased off of eBay. On this transformer, we had between 14.1 and 35.5% insertion loss. So that means that if you inputted 100 watts with 35% insertion loss, you only got 64.5 or 65 watts out here on 10 meters, and that is huge. So 14% to 35%. We changed capacitors on the transformers, and that's the only thing we did was just change capacitors to TDK 100 picofarad capacitors. We replaced the eBay capacitors with these, and we went from a 14.1% down to a 13.3% as the lowest insertion loss, and the highest insertion loss was 26.5% for a change of 9% better for 10 meters. But on 12 meters, we had an improvement of 10%. We went from 29.6% insertion loss down to 19.6% insertion loss. And the only thing we changed were the capacitors. Now we changed the type of winding. Let's move this out of the way a little bit. Still a 49-to-1. It's still a 14-to turns ratio, but now this one is tapped. It's got a single winding for the primary and the secondary, but it's tapped on the second turn, and it's a tight winding. As we see here, the windings are close together on both of these, whereas on the old transformer, the original transformer, it was wound like this, where we had the primary and secondary were twisted together the first 2 turns, then we had 7 windings, a crossover, and another 7 windings. So that's the difference between the original transformers, the first 2 that we did, and now this is what we're testing now. Let's compare the new transformer style just to the TDK, and here we had a loss of 0.59%, which we went from 85.1 to a 84.5 on 80 meters. So it went down just a little bit. We had just a little bit more loss on 80 meters, and the same thing on 40 meters. We had a 0.10% change there where it decreased. We had a little bit more insertion loss. We went from a 13.7 to a 13.8. On the rest of the bands, we had much more improvement over the twisted crossover winding compared to the tapped tight winding. Here at 20 meters we had a 1.71% increase. At 17 meters we had 2.61% increase. At 15 meters we had 3.87% increase. At 12 meters we had a 6.85% increase. And here at 10 meters we had 11.58% increase. So now, instead of 73 watts going out, we would have 85 watts, virtually a 12% increase in power. And here at 12 meters, instead of 80 watts, it'd be 87 watts. We got much more efficiency using the tight windings on these two cores. So there is more efficiency to be had using the same type cores that we have been using the TDK capacitors, and we can see significant increases in our efficiencies. In the next video we're going to be using different type cores. From everything I've seen, we're going to see bigger and better improvements in our insertion losses by going to these cores. It's going to be interesting. If you missed the first video, tap on the link that's going to be shown here on screen. You can look at the entire series we've done on these transformers so far. This is Kilo Mike 4, Zulu Kilo Bravo. Have a blessed day.